I'd like to first off introduce the chairperson for this session, who's organized something that I think is extremely challenging, Galen Shipman, Galen Arnold, I'm sorry, from our Science and Engineering Application Support Group. And what we're trying to do here is to launch a new program within the Blue Waters Project. And this was conceived a couple years ago at one of our reviews, and we call it the NICE P squared for NCSA, Blue Waters Extended Intellectual Services for Petascale Performance. And in that program, we instituted 3 components. The first component was for the NSF science teams. We provided funding to you in the first year of Blue Waters, actually starting a little bit before that, that we called the direct funding component. And we provided about a year of funding for a postdoc level position for most of you, depends on your university costs. And that allowed a number of teams to explore new ways of doing their applications. And our first Blue Waters Symposium focused on those teams and the results of that year's worth of work, and it was great, and we saw a lot of improvements that were desired and envisioned but not able to be carried out because the resources weren't there. The second component is the educational and outreach program, which enables us to have our fellowships, have our internships, have our virtual school, and a variety of other activities to work to build up the workforces, to expose more people earlier in their careers to really large-scale, petascale computing. And that's the other component. These are all from the Blue Waters Project funding. And we're happy at this symposium to initiate the third component, which is called Petascale Application Improvement Discovery, or PAID as the acronym. Those we couldn't figure out a water-based acronym, so we got a money-based acronym for this one. And this has really 2 pieces of the project. So we've engaged with a number of groups that some you know well from previous parts of the Blue Waters Project. Others are new to the Blue Waters Project, and we'll be introducing them here in this session today. We call these groups Improvement Method Enablers, IMEs, another acronym that we can use. But they're really experts in different parts of large-scale, high-performance computing and data. And they now are part of our project to bring their expertise and their tools and methods and make them available to the science teams and engineering teams on Blue Waters to possibly incorporate into how you're doing your science and engineering. So this session today is to introduce in very, very fast, short format all the IMEs. They're all here. A few will arrive, have some spokespeople here today, and some others are arriving, some other members of the teams are arriving tonight. They will also have posters during our poster session, so you can actually go up and talk to them. The major part of this symposium is to allow you as science and engineering team leads to engage with the IMEs to figure out, are there synergies that you might be able to use their expertise for in improving how you're doing your science, improving the productivity you have, the time to insight. Another part of this project is we will again offer some funding to a subset of the science and engineering teams. That process will define as we go forward. But those are basically the National Science Foundation PRAC teams that will have allocations at least through they'll have allocations from May 2016 on forward that already are there, or the teams that may be announced coming up. So the idea is that we will try to help you fund some of the effort to implement these improved methods and demonstrate them in your codes that then hopefully you'll be able to use for the future, not just on Blue Waters, but on other systems. And go forward with that. We'll try to provide some funding for the teams that are allocated through the National Science Foundation PRAC. The IME expertise is available to all of our teams, but the funding is only, because it's NSF funding, going to be to the NSF approved teams. We'll send you details about that. The funding will depend on how many teams there actually is eligible for this. But it'll be very similar to what we did before for the teams that were in that program before. It'll be very similar in terms of scale and in terms of expectation. So we hope that then there'll also be a separate allocation this time that for the teams that are going to engage in developing some new features or methods in their applications. We'll give some development time out of the innovative account for you to do the testing and development, not your production science, but the testing and development, so you don't have to use up your production science allocation to do that. So Galen is going to introduce these teams. We gave them each 7 minutes to make their points. And the first one is going to come in over the cell phone that we have here, and they will be here tonight. Thank you.
Hi, so I'm representing USC and Utah. We're a subset of the SUPR, which is a DOE SIDAC institute. My colleague Bob Wheeler might be in the audience. I hope he is. Anyway, so just real quick, we were told to introduce our team. So this is the SUPR team on the next slide. As you see, it's a lot of people. There's over $3 million a year of labor distributed over this team. And so if you go advance one more slide, what we're bringing to PAID is a small subset of the larger SUPR effort. So just not even all the people at USC or Utah will be involved, just auto-tuning people at USC and Utah. So if you go to the next slide, the basic deal in SUPR is that we assume everybody, everybody does have their own independent research. The money, if you think of the number of people I showed you a minute ago, the money isn't enough to, fund anybody. And so what SUPR does is it brings people together into a big collaboration, and then we find ways to integrate our tools, and the goal is to, have integrated research with results beyond what any one group could have done by itself. Let's see, so if you go on to the next slide, this one should have a graph. So this graph kind of is sort of a quick summary of the tools we brought together in our auto-tuning effort. There's a broad range of stuff. We have compilers, we have instrumentation, we have modeling tools so we can predict how well a code ought to be performing. We have active harmony, which allows us to traverse search spaces looking for optimizations. Oreo has that as well. And then on the right, where kind of all the arrows are pointing to the right in the spirit of all roads lead to Rome, in the end we have this thing called Chill. And Chill is a code transformation tool that can generate lots of different permutations of loops and other things. And so in some sense, everything on the left looks at code and tries to decide where there are opportunities for optimization. And then Chill generates the search. It generates all the instances that you would explore. If it's relatively small, you can just exhaust them all, try them all. If it's larger, then you can use active harmony or some other tool and try and search the space. So, for this collaboration with NCSA, all we're doing is we're bringing the Chill tool, which again, Bob Wheeler, if he's in the audience, he's going to install at NCSA on Blue Waters. And then our goal is to use it to try and automatically improve some kernels and some scientific codes. The next slide, the one that's titled SMG 2000, this one's my favorite example. SMG 2000 is a Litter More procurement benchmark, and it models one of their real codes. So what you see is basically on the x-axis is the number of experiments conducted, or that active harmony instructed Chill to conduct. And then as you can see, as we traverse this, there's basically a 500 million instance search space here. and we only generated, I think, 20 instances of that. And for the performance bottleneck loop that we extracted from the code, we got a speed up of over 2, and overall it's a quarter on the full application. So that's an example of what the full auto tuning system does. And there's a lot of human involvement in that, by the way. But as our research is to minimize that. Anyways, the last slide. What do we hope to do with paid? So the first thing is, today we only work with DOE codes, and so we're looking forward to meeting a broader range of scientists and their applications. Specifically, what we expect to do is to work directly with Blue Water staff to identify the suitable computational kernels, since we don't have the rest of Super and the rest of their tools to go try and do that ourselves. I'm assuming that Blue Water staff is very familiar with this. Likely candidates are dense or sparse matrix kernels, stencils. We've had success with geometric multigrid, so I'm sure that there are lots of examples like that. PETSI, for example, is something we've worked with before, and I'm sure there are PETSI appears in some of the codes Blue Waters. So we want to install the chill system, work with, again, the Blue Water staff to find good candidates, and perform auto tuning experiments. If we're successful, what we'll do is we'll offer up, optimized code variants back to the Blue Waters investigators. So you can take them if you're interested, or there's one example where we turned 50 lines of Fortran into like 2,000 lines of machine-generated, human unreadable code, and something like that might not be of interest. So whether or not you choose to accept these things is up to the individual teams. And Bob Wheeler should be there, and so at the poster session he'll be there, and you can learn more. So that's it. Any questions?
You had in one of your graphs a comment about CUDA and OpenCL. When you said code generation, were you thinking about like just-in-time type of code generation, or what were you referring to in the little page?
Gail, I'm sorry, I couldn't hear that. Could you repeat it, please?
So that was a question about slide 4 with CUDA and OpenCL. Was that just-in-time code generation?
I'll have to ask Bob Wheeler. He probably can answer that question. See if Bob's there. I think.
What we do is we take your loop and your construct, and we have a tool that will allow you to line up your iteration spaces and change the loop structure so that you can fit the topology of the hardware that you're running on. But when it comes to the CUDA performance stuff, what we do is, since a lot of people don't want to get into the details of how to get the CUDA code running, you can just give us your code, and then what you do is you provide us with what's a script that's written in Python. We take that Python script, apply the transformations, and some of the transformations are to CUDAize this particular loop, which it will then write out the code for the NVIDIA compiler and also the driver code so that you can just compile it and then run it. And I realize that that's not something, the GPUs aren't that big at Blue Water, but we can also take the tool and make it so that if you have, say, coarse grain parallelization that you want to do because you want to distribute it across nodes, you can do that and then dig down inside the inner loop and optimize that for a GPU or whatever you want to do. But if you have loops and arrays, and if you don't, I would love to hear from you because I'm going to lose a big bar bet on that there aren't codes that have loops and arrays. We can probably find a way to match it to the hardware in a very efficient way, and we'll help you get your code, tuned up in that way so that you don't have to spend time on that kind of stuff.
Okay, and our next speaker is leading a subsequence of speakers. Sanjay Kale will start us off talking about load balancing and scalability.
Thank you, Gil. As we all know, load imbalance can be a significant performance detriment. And in fact, as you increase the number of nodes that you use on Blue Waters or any machine, the risk that you lose a lot of performance from load imbalance grows significantly. And in fact, another additional complicating factor, of course, comes with its own benefits, is the fact that we have very powerful GPUs on many nodes, and that brings the issue of heterogeneous load balancing. Load balancing is something that we have been working on in my group for many years, maybe 15, 20 years. So in CHAM++, the measurement-based load balancing framework allows you to use recent past in scientific applications, engineering applications. There is continuity arising from various physical reasons. So a recent past can often, not always, often be used to predict the near future. And so you can do measurement-based as well as prediction-based load balancing. And so there is a wide variety of load balancing strategies that we have developed over time. So the idea in this project is to bring all that expertise to bear on broader set of Blue Waters users, not necessarily those using CHAM++. So what the framework provides is fully automated migration, when to call a load, monitoring loads so that we can figure out when to call a load balancer, what strategies to use, and the actual migration of objects. That's what is there in CHAM++. For MPI users, the first line of suggestion is to use adaptive MPI, which is an MPI implementation on top of CHAM++. And so that enables all of the fault tolerance load balancing features in MPI programs. This is an example of what someone did several years ago. They took the Brazilian weather code called BRAMS, and sorry, their names are not here on the slide, but Celso Mendes collaborated with Eduardo and several others to make this happen. But the point here is simply that as the storm passes through, the load as shown on the right on 64 processors keeps changing. And so you're going to get pretty bad performance as shown on the left figure at the bottom, where the utilization across the 64 processes is overall pretty bad. By over-decomposing this into 1024 blocks, and allowing the system to map those blocks to processors, we're able to overlap communication and computation and get pretty good load balance, as you can see on the figure on the bottom right. One of the recent things is, just as an example, the local DOE center called XPAC, it's a plasma simulation center. We demonstrated this MPI to AMPI conversion, and actually even without doing load balancing, when we do this over decomposition multiple blocks, you actually get cache benefits. So it actually shows that on 384 cores there, the over decomposed program actually gave performance benefit, load balance aside, just the over decomposition itself. So what do we want to do here in this project? Internally, we would build a newer suite of heterogeneous load balancers that balance work between GPUs and CPUs, and if scheduling strategies permit heterogeneous task delegation, we'll also worry about the fact that you might have a mix of GPU nodes and non-GPU nodes, but even without that, the GPU nodes, GPU-CPU balancing within those is self-challenging. So we'll build a generic library with a suite of load balancing algorithms that can be called from MPI applications. And so as long as you provide us with some blocks and allow us to track those blocks, we will tell you how to map those blocks and migrate them across processors. We'll plug in our load balancing strategies to make that happen for MPI applications. In addition, we'll also improve the support for converting MPI applications to MPI for those of you who want to take that route. The activities that we have planned where we would like your involvement is to assess the applications, identify the load, to identify the load imbalance problem. If you we'll work with you to figure out how much of a load imbalance problem you have. You probably know that yourself, but maybe quantify it some, and then help with appropriate libraries for load balancing. And of course, you'll have to do some over-decomposition of your blocks yourself. Of course, that's your application knowledge, but we can provide the complementary support by ourselves. So please talk to us on the poster on this topic. I think I should take questions on this, and then go introduce the next one. Okay, so that's all I have to say here. Questions? Yes? Yeah. Well, if you randomly move stuff around, yeah, okay. I think I understand your question. If you talk about one node and you look at what's happening within that node, and if you randomly dynamic, if you use OpenMP dynamic, yes, indeed, you're right. What we're talking about here is blocking for load balancing. In other words, instead of thinking of work as a uniform chunk, you think of it as over-decomposed sets of blocks. And then you work within one block, schedule it, work on it completely, then move on to the next block. Those blocks are still more or less statically assigned to processes for one outer iteration, but across outer iterations, they move. They can be moved under the careful control of a load balancer. So the point I was making here simply was that sometimes people say, isn't there a cost to over decomposition? And we say, yeah, there may be some minor scheduling cost, but it is very tiny, and you actually end up getting the blocking benefit of over decomposition in cache performance. Okay. Any other question? Okay, should I move on to the next? So and we probably need your help to set up that talk. While you're doing that, let me introduce the next two talks are going to be on the topic of topology-aware mapping. It's a topic that we have been working on for the last 10 years or so around my group. The Abhinav Bateli will be giving, from Livermore, who will be giving the second talk, did his thesis on this topic finishing in 2010. And we demonstrated the benefits a long time ago on OpenAtom, the quantum chemistry application on both Blue Gene and the old Cray T3D. But now what we want to do is bring all those strategies for topology-aware mapping together, and now that we have worked with Cray and Adaptive to get a topology-aware scheduler, how to bring those benefits to the broad set of users of Blue Waters. So first, Nikhil Jain, my student at Illinois, will talk about what we plan to do at Illinois, and then there is a separate project that I'm only coordinating independent of me that Abhinav at Lawrence Livermore Lab that Abhinav will talk about.
Hello everyone. So communication is one of the essential things which we have to deal with when you're running large applications or large set of cores. And typically it's something which shows up when you're going at large scale, when you're increasing the core count, and you start to see that your applications start spending more and more time not doing the actual CPU work, not churning out those DGEMs or doing the computation that you want, but start spending more and more time on transferring data from one end to the other. What can be done here? The thing is, if we know well about our application, and if we can do some of the work before your application begins or when your application is running, that amount of time which is spent on communication can be reduced significantly. Fortunately, the way MPI has been built, the PMPI interface allows you to collect a lot of this information and place them and do the work accordingly in a very transparent manner. In essence, if your application is written in MPI, which is the case for a lot of applications here, the PMPI library interface lets an external library like the one which we are developing interface your calls, collect the data that we need so that your application communication can be improved, and then subsequently make the real MPI application call. So what happens in a typical run is you write your code, you do not make any changes to your application code, you simply link in a library which we give to you, and when it's run, our app library will interface or intercept those calls and generate some report at the end, all transparently. This report that's generated is in some form which is human readable, so you can go through it if you want, but at the same time we plan to write automated scripts which can parse the data which is in in this report and come up with the information that is required. We plan to use this information, one, for performance analysis. This is something which you can also use. But more importantly, this information would be used to automatically categorize the job that you are running to a Blue Waters queue. So as Bill mentioned today, with the new topology or implementation, the queue being enabled, you will have multiple options to specify that my job is this kind of job, so this should go to this queue so that it can take advantage of topology in a particular manner. So this script or this tool will let you automatically do the categorization. We'll also work on coming up with geometrical suggestions. So based on the communication pattern that your application is playing, it can tell you what type of geometry or what type of grid will be the best for your application, so you can request the job scheduler to provide you that particular type of queue. And finally, it will also generate data which will be used for performing task-aware mapping both at the start of the job and during the execution of the job. So topology-aware mapping refers to placing your MPI ranks or your processes or charm ranks in such a way that the processes which are going to communicate more are placed close by. What happens, or what used to happen in a random allocation was, if you ask for 100 cores or 100 nodes, the job scheduler will simply try to find any 100 cores available to you and give them around. It's like taking the Blue Water system administrator team and placing them one each in one country in the world. Like, so one person in India, one person in US, one person in China, and then we'll say, go do your work. Of course, that is not the most efficient way to do your work. You want the entire team to be in one place or close by at least, and that's what happens here. We try and place them such that your communicating ranks are close by, and for that we are going to implement a number of algorithms. Some of them are generic, like a tree-based structure thing, or space filling curve, or a polynomial-based approximation scheme. All these schemes will essentially take the application's communication graph and the topology that is given to you and place them such that the communication is minimized. For more structured algorithms or more structured applications which have common geometry, such as if you're running an application which has a 3D grid running on a 3D grid of Blue Waters, or if you have something which performs an all-to-all communication, better things can be done, and we'll be working on implementing algorithms which will do that. Finally, all these schemes and the tools that we'll talk about will be fully automated. So in some sense, what the applications will need to do is do a very small run of your application for, let's say, 10 minutes, 15 minutes. Let the profiler generate a bunch of profiling file, and then submit your production run. At the beginning of the production run, the profiling tool will take up those profiling files and generate a nice mapping-aware placement scheme for you, which will be passed to the scheduler, and then the scheduler can place your job accordingly. So hopefully with these setup, without making any change to your code, you will be able to reduce the communication time. What we are looking for from our application team is this. If you are not sure that your application is communication bound, or if you are not sure which Blue Waters queue is best for you, then please come and talk to us, and we'll try and test or use some of our tools on the applications that you have and come up with the right answers for you. Also, if you're not sure if topology or mapping can improve performance for you, do come to us. More importantly, if you know that topology or mapping is something which you care about, then we can help you come up with good mappings that can benefit your production runs. In the past, we have done such things for a number of production applications. I've listed 3 examples here. NAMD has been using topology over mapping on BlueJeans system and Offlet on Blue Water system, and it has shown performance improvement of up to 25 to 30%. OpenAtom, which is a charm code, I wrote some of the topology mapping for them recently, and we have seen performance benefits in the upward direction of 40%. And then MPI applications like Milk and PF3D, using a tool called Rubik, which Abhinav will explain very soon, we have seen performance improvement up to 25%. So overall, whenever we have seen an application which is communication intensive or which becomes communication intensive, a large core count, the performance improvements are easy to get and they are significant. So what we expect is, or what we rather hope is, in the poster session in the evening, you can come and talk to us, and we can try and see how to make sure that topology-aware mapping can help your application. Thank you. Next up, Abhinav will provide more details on some of these tools and some other work that Livermore will be conducting as part of PAID project. Oh yes, so that's true. Questions? Yeah. we've seen is if your application has something like an all-to-all communication. So as your application does more and more communication patterns, so something like all-to-all, you'll probably start seeing the effect within a few hundred nodes. For example, for OpenAtom application, which does FFTs because it has to do DFTs very frequently, at 128 nodes, we see a performance improvement of around 45%. So it can be as low as that. Just it depends on what communication pattern you're applying. Where for something like NAMD, which has near-neighbor communication pattern, the improvements start to show up more like at 1,000 nodes. So it's completely dependent on how your application makes use of the network.
This is related, but maybe it's a little bit off. There's been some suggestion that memristors might be useful in this regard. You have co-located co-located memory and CPU. So how will this affect your work in the long term?
I actually co-locate which things, CPU, RAM.
Memristors. I think that is more about memory bandwidth than across node communication. There might be some complicated second order connections there, but mostly here we talk about interconnect topology thing, and I don't think it will affect interconnect topology for communication.
Any other questions? Thank you.
Hi, I'm Abhinav Bhatele from Lawrence Livermore. So Bill and Sanjay and Nikhil already gave a good introduction for the work we are trying to do here. We are going to leverage a lot of the work we are doing at Livermore. We have a LDRD project on task mapping. We have various collaborators at Illinois, Utah, and UC Davis who help us with a lot of the visualization tools that we use for our task mapping, and I'll talk about some of those things. So process placement or layout can improve application performance significantly, as we saw in Nikhil's talk. We have developed two tools at Livermore. One of them is called Rubik. Rubik can be used to map applications if they have a structured topology in terms of their communication. So for example, if you have a physical domain which is decomposed into the MPI process grid in a n-dimensional Cartesian space, and then you have a network topology that is also n-dimensional. So if it's 3D torus for BGP or Cray, or if it's a 5D torus for BGQ, we can take the application and map it to the torus of the machine in a certain fashion depending on the metrics you're trying to optimize, be it latency or bandwidth, and we can improve performance. So Rubik works for structured applications and structured n-dimensional topologies. We also have another tool called Chizu, which is a more generic tool. It uses graph partitioners. So we can use graph partitioners like Metis or Scotch to partition your application graph and then the network topology graph, and then do a one-to-one mapping or a recursive mapping between those two graphs to give some performance. So this works for arbitrary application topologies and arbitrary network topologies. We'll have some performance results in the poster, so hopefully you'll come and talk to us there. We are also developing visualization tools to look at network traffic. So this particular visualization is showing the nodes of Hopper, which is a Cray XT machine. And in different colors, we are seeing different jobs. The constant between the two images is the blue job in the middle, which we were running on a contiguous partition. And we had other jobs running around the blue job. So the performance of the job on the right side was about 25% faster compared to the job on the left. And this was mostly because there were two other jobs running simultaneously in green and red that were encircling the blue job and increasing its communication time. So we have tools such as, so this tool is called Boxfish, and if you have the queue state for when your job was running and when other jobs were running, what nodes they were running on, you can visualize the placement of your jobs and figure out if that is a problem for your performance degradation. This tool can also visualize network links. This is for the 5-dimensional Blue Gene queue. We are showing 3 of those dimensions, and you can see the number of packets going over various links. So the red packets, the red links are the ones that are the hotspots, blue is low and less traffic. So that can probably help you figure out if network congestion or hotspots are leading to performance degradation. So this is a tool called Boxfish. It's available on GitHub on Livermore Scalability site. The other tool we have been working on recently is for the Dragonfly machine. So this is Edison at NERSC has the Dragonfly topology, which is a hierarchical multi-level all-to-all. And so in a circle, we have arranged the nodes in the system, and between the routers on the system, there are links, and then we can selectively look at links that are highly overloaded with packets. So you can figure out that there are some links in red in the lower left corner that are a performance bottleneck. For within the node, within group links, we have other traffic shown in the matrices on the right. So both of these tools can be used to look at the job placement of how jobs are being mapped to the machine, and then also look at the link traffic if you have the network counters information available, which I believe is the case for CRAE systems nowadays. The other related project that we want to work on is applying machine learning to HPC performance data. So we have been using regression and supervised learning to find correlations between hardware counters, specifically network hardware counters and performance. We have applied this to Blue Gene Q network counters so far. So in the image, we are looking at different counters on the x-axis, different applications on the y-axis, and which counters are important in affecting the performance of different applications or application sets. On the Blue Waters machine, these admins collect performance data using LDMS, which is a monitoring tool. And so in this project, we want to look at this performance data and do some machine learning analysis on this. I believe there is about 1 year of data. It's in terabytes. There's a huge amount of data of which applications were running when, what were the hardware counters on the machine, and hopefully we can figure out if co-location, sharing of links affects performance, and what can we do to improve it. So we'd like to identify application codes. So if you have an application that is heavy in communication, examples are things doing lattice QCD computations such as MILK, quantum chemistry applications such as QBox, and several other applications have heavy communication. So I would say if your application spends more than 20% time in communication, maybe we can optimize some of it by doing a nice placement on the machine. And finally, we plan to collaborate with the Blue Waters admins to look at the LDMS data and do some machine learning analysis. Thank you. Questions? Yeah.
Okay, you can probably hear me. I'm curious about your application of machine learning in this activity.
Mm-hmm.
What did you have in mind? Is this supervised, unsupervised machine learning? What kind of software are you thinking about deploying, and what's your goal?
So far we have been using supervised learning. We have used various algorithms like SVM, extremely randomized trees, gradient boosted regression trees. And what we do is we collect some performance data, use it as our training set for the model. And our independent variables are the network hardware counters that we are collecting. The dependent variable is execution time. And we want to see if there's a correlation between the independent features and the execution time. And then identify which features are important. Is it the injection bandwidth on the links? Is it the actual links, or is it the buffers on the intermediate nodes? And that gives us a better idea of contention and how it's developing on the machine.
So as supervised machine learning, are you working in particular on what kind of classifiers are you identifying new kinds of classifiers in an SVM type?
So I'm not a machine learning expert. We have mostly been using existing algorithms. We're using regression analysis, and we've been using scikit-learn, which is a Python toolkit for doing this analysis. Thank you. Any other questions? Thanks.
Okay, next up we've got Bill Gropp, who's going to talk to us about scalability and parallel I/O performance.
Thanks. So this is really two separate sub-projects, but they're related by a sort of common understanding of the problem, which is that the performance problems that you sometimes encounter are not always where you think they are. Sanjay's already talked about load balance and its impact. I want to talk a little bit about some different approaches to dealing with the load balance. And in fact, Rudy, we have an answer to your specific question that's focused immediately at things like OpenMP and the cache impact of doing better scheduling. Also want to look at better ways or more efficient ways to improve I/O performance. This is an area where, as you'll see on a table, plus if you come to the poster, I have some more results. There are the many low-hanging fruit here. So just want to emphasize that there are lots of sources of load imbalance, even applications which you think are perfectly load balanced rarely are in the real world. So your application might be perfectly load balanced, but the compute resources that are provided to you through the cores may not be uniform, may not have uniform compute power given to you, because there are all sorts of other things that are calling on those systems. So the OS, the runtime, may share the core, they may share memory paths, they may share the network. All of those things will impact the effective load balance of your application. Additionally, other applications are sharing the network unless you're using the entire machine. You may find that your communication is impacted by other applications doing communication, other applications doing I/O. The topology-aware scheduling helps to reduce the impact of that, but it doesn't entirely eliminate it. And even applications that like to argue that they're perfectly load balanced often aren't. There's often extra things going on at the boundary conditions or other parts of the application which give it a slight imbalance. There are lots of tools that are available to explore. We have some tools already, and they're easily customized to focus in on things needed by specific applications. So one of the things that we're interested in finding out from the teams is specifically what are they worried about, what do they think might be an issue, and then we want to look at how best to form hypotheses about the problems and answer those problems. There are, as I mentioned, some tools. There's also a new interface in MPI, the MPI-T interface is part of MPI-3, currently not exposed through the Cray implementation, but that should change over time. Plus, it's possible to use other systems to examine the impact of some decisions in the application with this. And this is a standard part of MPI, so it'll be available on any system running MPI-3. Among the approaches that can be taken to address the load imbalance, one is to make use of the hybrid model. So for those applications that are already using MPI plus OpenMP or MPI plus OpenACC, this allows you to more easily shift work among the cores. You do run into this issue of loss of core locality, which was mentioned before, but there are techniques which have shown that by including information about locality and by using more carefully arranged scheduling systems, one can get the sort of core locality that you need for performance while getting the benefits of being able to adaptively shift work among the cores on a node. If you're interested, we have some more details on our poster. This is really appropriate for applications that are already using a hybrid model or are thinking of adopting a hybrid model. Might change the way you want to think about it. So again, it's a good time to come see us. In addition, for those applications that want to stick with a pure MPI model, one interesting possibility is to use what some people have called MPI plus MPI. MPI-3 allows you to access shared memory, which you can use the way you expect with shared memory. This again provides you with a way to shift work among the cores on a node or on a chip fairly easily without necessarily restructuring large parts of your application. And in this case, since the MPI processes on a node share the memory, it becomes a little easier to adapt to load imbalances that are restricted within a node. And then Finally, one thing that we're interested in seeing how much interest there is, we'll often use mesh partitioners to try to get a good load balance. The problem is that these are all based on some sort of cost model for doing the partitioning. And there's a wonderful phrase that all models are wrong, some are useful, but these models, first and foremost, are wrong. They're somewhat useful, but they are wrong. And so understanding how to adjust the partitioning to more accurately reflect the true cost of both the computation and the communication is an interesting problem, and it's one we're interested in finding teams that might be interested in exploring this direction as well. Now, as I mentioned, I/O performance is a place where there's lots of low-hanging fruit. Here's a simple example. In fact, I use this in the course on designing and building applications for extreme scale systems that I just taught. It's a very simple one. We use 1,000 processes. We're going to write a 16K by 16K array to a single file. This is only using 64 nodes. And if you write it in the simplest possible way, which is each process writes out its piece using the default parameters, you achieve a sustained bandwidth of about 2 megabytes per second. If you do it by using MPI collective I/O and a better selection of the default of the parameters, you can achieve over 1,000 times faster, about 3.8 gigabytes per second. So that's a fairly straightforward change, gives you 1,000x improvement in performance. We're also currently collecting data on the use. You've heard about, I think you've seen messages about Darshan. When I submitted these slides, we already had about 70,000 runs. This data will allow us to get a better sense for how applications are using the I/O system and help us to identify places where we might be able to help. I should point out that a set of data coming from some other supercomputing centers has already been examined, and it became clear that there are no easy answers here, that the common I/O patterns that people use range everywhere from usually just pretty good, maybe not great, usually from pretty good to completely awful. And there's no very simple rule of thumb. So again, we'd like to talk with you about what we can do together to address I/O performance issues. We're going to be using this Darshan data to help identify the applications. Again, we may extend some of the profiling tools to make it easier for applications to identify exactly where the greatest potential benefit for making some change in the I/O system is present. There are a number of things that have been explored, including tuning some of the I/O parameters, including the use of auto-tuning within, for example, HDF5. There are tools to provide buffered I/O or a different kind of model for I/O operations. And sometimes the most important thing, though, will be to restructure the code to use collective I/O and adapt the entire application workflow to better match how you can get the best performance from parallel I/O. So, in summary, these two projects are looking at places where performance is often lost in ways that may not be obvious. The rules of thumb on fixing these don't always work. They may require some changes to the code to address load balance and I/O, but I want to emphasize most of these changes would apply to any system, not just Blue Waters. The specifics are going to depend on your application, and be happy to talk with you at our poster. Thank you. So, do you have questions? Yes.
So, are there existing tools or software out there using the MPI tools interface?
There are some tools now. Okay, so the question is there anything that's using the MPI interface? There's starting to be some tools that do that. There are tools, for example, that can help you identify the variables that are available. There are tools that are being developed, particularly groups at Livermore, that are starting to use these to get more information out of the MPI implementation about things like how much time was spent waiting for communication to complete. There are other places where, for example, the MPIT control variable interface can be used to allow you to override a selection of algorithm for the collective communication algorithms. So you might be able to optimize those over the defaults that are picked in the implementation, so forth. So they're just starting to be used.
So it sounds like it can go beyond just basic profiling like MPIT.
Oh yeah, so the MPIT interface is intended to give tools and developers access to very low-level performance and control counters within the MPI implementation in a way that is just inaccessible through the MPIP interface. So a lot of implementations will have their own, for example, performance counters that they use for tuning the implementation. This interface was designed to allow the MPI library developers to expose those things. Similarly, the variables that control the choice of, say, poly algorithms for the collective routines or the eager threshold for point-to-point, those are accessible through the MPIT control variable interface.
So next up we have Jason Larkin, who will explain Spiral FFT.
Good, thanks. Yeah, so I'm Jason, and I'm an engineer at SpiralGen, which is, I can't walk away, is formed out of the Spiral project at Carnegie Mellon. I'm actually giving the talk for Franz Franchetti today, which I think maybe some of you are familiar with. He's actually our CTO, so he shares a dual hat in this project. And the project is really a collaboration between the two entities and also with Blue Waters. So Spiral was created a while ago to address the need for automated code generation, and in particular to address the problem of this explosion of architectures and heterogeneity, which I think you guys know about from Blue Waters. And to answer the question, how do we get optimal or near optimal performance with minimal coding effort? So this is what the Spiral tool itself addresses. We at SpiralGen have been taking this tool in particular for FFT generation and creating a web or cloud-based interface to this tool that provides sort of a single front end to the many backends which it supports, from x86 to ARM and others, and also to supercomputing platforms like Blue Waters, which is the focus of this project. So Spiral FFT is built on the Spiral tool. And the Spiral tool is a code generation tool which begins at a symbolic representation level. So on the right, there's a discrete Fourier transform of size 4, and the Spiral system, which knows all the sort of tricks about making code fast. And it's sort of a closed loop system, is able to generate fast C or Fortran code. And actually, with this system, able to generate much more than just Fourier transforms. In fact, there's about 1 million lines of code in Intel's IPP, which is automatically generated by Spiral, which is fast, as fast or faster than handwritten code. So Spiral is capable of much more, but of course the focus of this project is on FFTs, and Spiral has a long history of doing well on with FFTs on supercomputers. Back in '06, it was a Gordon Bell Prize winner. on the BlueGene platform. That was a project-driven piece of work. They did some electron structure calculations. Again, in 2010, another BlueGene P machine Challenge Class 2 award. And then recently, one of Franz's students, Tom Popovici, was able to, again, take a particular project, in this case, the linear scaling density functional theory code, 1TEP, and implement an optimized upsampling FFT algorithm to see about a 3 to 5 times speed up over MKL and FFTW. So I highlighted that work in particular because I think that's the sort of direction we want to go with this project on Blue Waters. Of all the things that Spiral can optimize for, it provides a very large sort of design space, one that's maybe intractable given the scope of the project. So there's some low-hanging fruit right off the bat for us, but I think in the long run, we would like the selection of which of these things we optimize for to be project-driven. That way we can narrow down what it is we actually do, optimize with respect to. If you want to see some performance, come and talk to me at the poster session if you want to talk specifically about your project and about what we can do. And I can take questions there, and also now. I think maybe that was a bit fast. Yeah. Because we can talk at the poster. This is a fast thing, right? So are there any questions? Oh, sure.
Where can one run your tool?
So I'm not sure if we're allowed to give out. I think based on the statement of work, we were allowed to distribute to those in the audience, those on Blue Waters. You can run the code locally. We support Linux, Mac, Windows. But in the future, we want to offer the service through our web base, where you can use the tool at all the way up to this level, the symbolic level. But I suspect many don't want to use at that level. They just want fast code. And that's supported in this, will be supported in this interface as well. We're actually developing this interface in coordination with a few other projects, notably 2 DARPA projects. And in those projects, they want access at that level. And actually want to bolt on top of that level some other formal methods, type methods that do proof verification. So really, this project also could help to steer the direction of to what extent we offer that through this service and what interest there is, in particular from this group. Any other questions? Okay, thanks.
Next up, we've got Quincy Koziel for HDF5. We'll give Quincy a plug right now for being the first person to get his lightning talk prepared for presentation after the call for lightning talks. Good job.
Morning all. I'm here this week with Scott Breitenfeld from our team at the HDF group. We're here to we're from the HDF group. It's a nonprofit company. We spun on NCSA about 8 years ago, so we're NCSA alumni in some sense. Our goal is to support, sustain, develop the HDF technologies, including HDF5. HDF5 is an I/O middleware package that's designed to address the data challenges that applications have, particularly in the sciences, although it's been used across enormous varieties of other domains as well, finance, people tracking, all kinds of airplanes, everything that's going on out there. If you've got some needs for storing your data on Blue Waters and other systems, we popularly support all the DOE platforms that are out there pretty much, and you have very large, very complex data, you're pushing the limits of what the application platform can support. This is what we've designed HDF5 for. We started about 20 years ago. We've got a lot of experience going in, and we intend to continue on for the long term. HDF5 is also designed to make certain that you can move your data around between all those platforms, and the software is also extremely portable. We've had it ported from feature phones up to, you know, the top 500. So you can carry your data and your software anywhere you'd like to go. We work extensively with tool developers all across the spectrum, lots and lots of open source and commercial tools, you know, folks from Visit, MATLAB, Mathematica, R, all the different places in the spectrum that can access data and have a good place to write an HDF5 interface. We work with these guys as well. And finally, we want you to get your data back in the long run, if that's important to you. Most people it is. As an example, we work with NASA. They store their climate modeling data from the satellites, or the climate observational data, actually, from the satellites, and they need this data back in 50 years. We intend on, you know, writing the software and the maintaining things for that long. We, as I say, are not NCSA alumni, so here's a HPC success story. This was run on Blue Waters. Basically, the whole machine at the time, it's a 10 trillion particle plasma physics simulation from one of the DOE apps that we work with too. It achieves approximately 50% of the peak practical performance on I/O for Blue Waters. The actual raw bandwidth is higher, but this is very, very difficult to achieve in a good application, but we're pushing the limits as far as we can. It's part of our goals for the project too, is to keep pushing those limits up. We've got a release coming out later this year that we've been working on for a few years, and some of these features are from DOE projects and other NSF work, Blue Waters and other ways. There's a number of scalability factors that keep getting revealed as we progress through newer, faster, bigger storage systems. So the first couple of points here about removing this and collectively reading and writing metadata, that's kind of addressing scalability over time. It's a 20-year-old piece of software. We have to keep moving forward. A couple of new projects, new features that will be coming in are the ability to access, read and write HDF5 data sets and do that in a single collective operation on multiple data sets. So if you've got pressure, temperature, whatever other fields you're monitoring in your application, you can write all that data out in one single I/O call and dump it all down to the I/O system, and then it'll all go out at once instead of breaking it all up into separate calls. And we're looking to add support for compression in parallel, and this is something that people keep asking us for. We'd like to get that finally out the door too. We're also working on a feature for advanced concurrent access to HDF5 data, where a single writing process, or an MPI application in this case, can be writing data out simultaneously while readers are coming in, so you can analyze and monitor the application as it's going along, writing the data out. No locking, no concurrency limits, as long as you've got a good parallel file system, and GPFS, Lustre are fully capable of doing this. You can do these things in parallel while the app is running live. We're here to work with you guys. We're really very focused. As I say, we're a nonprofit. We're very mission focused. We want to help serve the HDF community and reach out to you guys. If you've got anything that you would like to talk to us about, we'll be hanging out at the poster session, trying to get all the information we can. We want to help you assess what your applications are doing in the IO space, help you work with HDF5 if you've got a problem or you got a feature that you'd like, or some performance aspect is a problem, and maybe you want to start diving in and getting support for HDF5. That's a great way to get involved too. So any questions on any of the HDF5 things, or just talk to us at the poster. Again?
The compression in parallel, is that node-based or MPI?
This will be MPI. If we can leverage the GPUs, that'd be great. That's the only place I can find for a GPU in an I/O application. Anyone else? Yes? Thank you.
It's wonderful that you use Python too. It makes you so easy to look at your data and pull it up really fast without having to have problems with accessing your data. So I think it's really beautiful for being able to get a lot of things done fast.
Super, thanks. Plug for the Python wrappers that we work with, guys. There's also a new Python visualization browsing tool that we've got that's called Compass that will be coming out soon, and lets you do Python scripting natively in the Viz tool, too. So. Okay, yes, ma'am? Yeah, 50 and 100 for them, but yeah. Well, we've got, we're very software engineering focused. You have to be in order to maintain high quality software for long periods of time. And we've got a number of different, I guess I would call them development patterns that we use internally for maintaining full backward compatibility. You can read HDF5 files you created 20 years ago. With the current software, the current library is just fine with that. And that's part of how we intend to evolve into the future as well. We expect that the data that you're creating today will be able to be read in a long time from now with our software. If necessary, we'll continue to evolve. Right now we're still in a C library, but it'll evolve maybe someday later into something unknown that we don't have. It's really truly a backward compatibility and the software engineering to keep it running properly on all the platforms going forward into the future. Thanks.
Next up, we've got Simon Garcia de Gonzalo. He's in Wenmei Hu's group, and he'll talk to us about using accelerators.
Hello, everybody. So my name is Simon, and I'm in Professor Wednesday group. He couldn't make it for the lightning talk, but he will be available later this evening to answer any questions you might have about this talk. Basically, the purpose or our involvement of our project, of our research group in this project is basically to make sure the scientists, the application developers are actually having and actually using effectively using the accelerators available to them. And we are going to go, and we're trying to aim for that in two ways. First, we are making full use of the standardized interfaces available, and the community, sorry, I'm a little sick, and the community compiler technology to introduce the science teams, the accelerator-based libraries for the scientific tools. And by that, what I mean is that we're writing accelerator code in a higher level programming model, so they don't have to deal with all the little nitty-gritty details that it usually takes to write good accelerator code. The other way we're offering our help is basically by providing expert support. And how we're gonna go about doing that is basically we're gonna be holding workshops for the scientific teams, where we're going to help them take advantage of the accelerators available to them, and also we're going to be also providing some more individualized collaboration with the teams. We're going to also make available to them so we can have a more one-on-one with the teams, so we're making sure that they're using everything available to them. So the people you see up here are basically the students or the parts of the group that are involved in this project. From left to right is John Larson, Li Wen Chang, Isat, and Carol Pearson. So there's kind of a lot of tools I would wish to talk to you about, but due to time, I'm going to kind of concentrate on two and then kind of briefly mention some other ones. The first one I want to talk about is basically C++ AMP, which is basically, it stands for C++ Accelerator Massively Parallelism, which is a programming model which allows you to express data parallel algorithms in C++. So if you were to compare C++ AMP with lower level programming models such as CUDA or OpenCL, C++ AMPs allows you to kind of encapsulate all this this data movement that you don't want to really deal with when writing these applications. So encapsulates a lot of these details away, so makes your source code slightly slower, much easier to read, much easier to write, etc. And the other nice things about C++ AMP is basically that allows you to keep within the object-oriented framework or environment that C++ provide that promotes productivity. So a lot of the issues with writing code for accelerators is that then you have to move away from an object-oriented idea and then flatten out a lot of your objects to make use of accelerators. Well, we don't want to have you to deal with that, so we're going to help you understand how to take advantage of C++ AMP so you can take advantage of accelerators. The other thing it does is also gives you some tuning elements, so that very much like if you ever use OpenMP or OpenACC, allows you to tune your algorithm or your application for specific hardware, So very much like OpenMP, you will add some specific pragmas to help the compiler do a better job. You would do the same thing with C++ AMP. So the C++ AMP multi-core commercial grade compiler that we are using was originally built here, at Illinois, and it was first developed with GMAC technology, which was the technology that took care of moving the data back and forth from the host and the device. And this technology can easily change, so can be applied to when we're moving from CPU, GPU, on-chip technology. So your source code won't change as the hardware beneath it does. So that's the other good thing about it. The other tool I wanted to talk to you about is MXPA. MXPA is basically a fully supported OpenCL compiler that retargets your code based on the hardware you're running it on. So let's say you took the time and built an OpenCL kernel for some specific heavy computing section of your application, and then you're running on Blue Waters, and then instead you got assigned, you were fine with what type of node you were picking, and you got assigned an XC node instead of an XK node, but you still want to take full advantage of your OpenCL kernel. So what we do is that we take a look at the locality-centric scheduling approach, where we look at the access pattern of your scientific applications, and based on that, we schedule the total OpenCL work items, or the threads, in a way that we make the most out of the locality, and therefore we get better performance. And we have shown that we do better than the Intel OpenCL compiler and the AMD OpenCL compiler in many different cases. Here's a quick graph of many different benchmarks, Parabol, Rodinia, and some others. And generally, we do better than other vendors out there. So we'll be helping you take advantage of MXPA as well. Other things that I'm only going to briefly touch on is OpenACC and NVIDIA Thrust C++. OpenACC is very much, if you ever use OpenMP, you will know, and you will kind of know how to use. And the nice thing about it is pragma-based, so you can just help your code along without having to rearrange or recode your scientific application, but helping the compiler do all the hard lifting. So we'll help the application developers be able to take advantage of the accelerator this way if their application is better, is used better with using OpenACC pragmas. NVIDIA Thrust, very similar to C++ AMP, is that there is a lot of basic blocks for many scientific applications or many algorithms that use the same kind of sorting and other types of small algorithms that NVIDIA Thrust already takes care of it. So we want to make the developers aware of what's there, so you don't have to reinvent the wheel. There's already a very fast sorting. You don't need to write it. We'll help you understand where it is, help you embed it in your code. And NVIDIA Thrust has really good types of these building blocks that you can have basically for free. You just have to call them. But basically, working with us, working with the impact groups, we have a very strong background in helping scientific application developers learn and take advantage of accelerators. We have very good experience with the virtual school for computational science and engineering, where we teach hundreds of scientific application programmers and developers to use accelerators. We also have the POM Summer School that we have a lot of experience with in collaboration with the Barcelona Supercomputing, where we help developers all over the world come with their code, and we help them develop and change them so that they can take better advantage of accelerators. So we have a lot of knowledge, as well as porting real-world DOE applications. In the last 2 years, we have had a lot of experience in this area. In this summer school, we do teach lower-level programming models such as CUDA and OpenCL. But we do think it's important for application developers to know at least the basics, just because if you're very performance critical, you might want to have to write the code yourself and let the compilers catch up. So it's important to know how to develop CUDA code or OpenCL code, and we're very familiar with helping you guys learn them and take fully advantage of them. So the real objective of this collaboration between the Impact Research Group and the Blue Waters collaboration is basically to do more science in less time. And we have this feedback loop going on between our group and many of these developers. So while you take advantage of the tools, we learn what they're missing, and we go back and we talk to NVIDIA, we talk to PRAC, PGI, and we tell them what they're missing. And so therefore, we've built this loop of mutual cooperation where we keep the tools becoming better and better, and you benefit out of them. So in other words, we improve communication tools and libraries. So with that, I'll leave for questions and any questions you might have.
Next up, we have Bill Tang, who will talk to us about accelerating PIC codes.
Well, thanks, Galen, and thanks to Bill Kramer and colleagues here at NCSA for giving us the opportunity to participate in this, I think, quite exciting program. This is obviously a very large growth area and very challenging best practices dissemination for petascale applications, improvement, discovery. Let me just, with the short amount of time that we have, what we're trying to bring into play here is to share our experiences in a particular tool application area, particle and cell codes, which are actively utilized in the plasma science application domain, fusion energy science and such, but also is used for astrophysical science applications, space plasma physics, and many others. And there's commonality with certain aspects of even MD simulations and such too. And so first of all, we're at Princeton University, myself and my colleague, Dr. Bei Wang. She's the lead software developer for this project. And we're at the Princeton Institute for Computational Science and Engineering, interdisciplinary institute at the university. The particular software that we're working with is the so-called Global Toroidal Code at Princeton, GTCP. This is a very highly scalable, three-dimensional particle and cell PIC code that's used for studying microturbulence in plasma and fusion systems. But the aspect of this is that we focus on this as a particular example application area, and what we want to share are experiences in porting and optimizing this code onto a wide range of multi-petaflop platforms worldwide at full or near full system capability. I'll show you a figure in a minute. So the code portability is aided by the fact that this is not critically dependent on any third-party library, so it is highly portable, and it'll give people an experience, if you will, on how this performs on a variety of challenging platforms. Here's a quick view graph of this. This code has been ported to and has worked well on the top 7 supercomputers in the world. And we also have, and this shows how much of peak performance we've achieved to date. This is still a work in progress. And I think the shared experience, the lessons learned that we get out of working on such systems can be very valuable to share with the Blue Waters application community. So, so in particular, in terms of quote-unquote success story type figure, we'll come to that in a minute, but some of the elements that this incorporates are domain decomposition, two-dimensional domain decomposition, plus particle decomposition for increasing scalability, reducing the memory footprint as you go to tackle larger and larger problem size. This capability, this software capability, is really focusing on being able to handle larger problem size. And larger problem size, there are no free lunches here. You have to be able to engage computing at extreme scale to enable you to acquire the resolution that you need, plus what Bill Kramer also mentioned, to enhance time to solution. And so one of our main focuses in developing these capabilities, and we haven't developed this just at Princeton, we've had long-term partnerships at the other leadership class computing facilities over the years with the Lawrence Berkeley Lab group, their Future Technologies group, and with very active and very fruitful collaborations at Argonne National Lab, at Oak Ridge National Lab, and at foreign facilities, including more recently in the past year or so with the #1 machine in the world, Tanhut 2. So this involves things like the proper choice of data layouts for maximizing data reuse, hybrid programming models, leveraging GPU and Xeon Phi accelerators. These are all quite interesting, and there's a lot of important messages that one encounters as one deals with such systems. And let me show you just real briefly. These are examples of some results across a lot of prominent large-scale machines. And of course, I don't have time to go through this in great detail. The vertical scale is wall clock time per ion step size. These are particle codes, and this is the number of nodes on the horizontal scale across these various systems, both emphasizing the CPUs as well as the GPU performance on some of these systems. Please come to our poster. Dr. Bei Wang will be holding forth at the poster, and we can answer some more specific questions. So you want to look lower on the scale here for the faster wall clock time per ion step. And there are reasons why these systems give you somewhat better performance as you look at these things. One of the lessons learned, for example, is that the communications, the most modern communication system, the Aries Dragonfly network, at least for this class of codes, these particle and cell type codes, really makes a significant difference. And so one thing that I'll comment on listening to the very interesting presentations in the PAID program that preceded my talk here is that in listening to what Bill Gropp was talking about, and also from Wenmei Wu's team and such, I think as we develop our capabilities to be able to help the applications domain for the greater Blue Waters community, that we will also be learning as we share experiences with our other team members in this PAID program. For example, if it turns out that the improved performance that we observe because of the improved communications capability that's built into the Aries Dragonfly network, then I think some discussions with Bill Gropp and his people would be very interesting to see Right now, this is not the system that you have in place in Blue Waters, but there are other ways to address these issues, and we're very interested in exploring that because, in fact, on both Titan and Blue Waters, which are very similar systems, you have large user communities that would benefit from improvements along these lines. So the services provided that we hope to be able to provide, this is the last slide. Overall goal is to leverage our experiences and lessons learned from the development of this piece of software. We have experiences on Blue Waters already, and as well as on the other large NSF system, completely different type of architecture, the Xeon Phi Stampede system, largest one in the US, the Xeon Phi systems. We also, as I said, have benefited from linkages to abroad, to the Tianhe-2 people in China. The specific focus is to accumulate, create, and apply best practices for efforts and services of Blue Waters application teams, emphasizing what? We also have experiences in terms of looking in the application domain, the coin of the realm is what? Time to solution. So we want to emphasize how can we help communicate better practices to enable that. But the other thing that's interesting is also what is the energy to solution? How quickly, how much energy is expended as you carry out these calculations? We will more specifically develop applications that effectively utilize multi-core and many-core systems using a single code with appropriate interfaces for multiple architectures. We will explore directives-enabled GPU kernels using OpenACC and the new OpenMP4 to improve portability and share with our Blue Waters application teams to help inform their work planning activities as they move forward. So this is a very dynamic, forward-moving activity that I think is quite exciting. And basically lowering the threshold for efforts needed to re-engineer Blue Waters applications to improve usage of accelerators and many-core. So please come to our poster. We'll be able to talk to you more about these things. So I'll stop here.
And our last speaker is Steve Tiki, who will do a quick demo of Globus Online.
All right. Hi, I'm Steve Tiki. I lead the Globus project. So I'd do just a real quick intro for those of you who don't know what Globus is, and then give a real quick demo of how it's used on Blue Waters. So just quick show of hands. How many people have actually used Globus to move data around at this point? Wow. I don't have to do much of a demo then, so most of you have seen it. So I will go through real fast and highlight a few of the newer things that you may not have seen. We'll also have a poster tonight as well, so if you have questions or comments or suggestions of things we could do better or things we're doing badly, whatever, or things you like about it, come by and let us know. So Globus, our mission is providing a service to help you manage your data through its life cycle, to schlep your data around, to share it with your colleagues, all that. So the first capability we have, I'll show, is data transfer. So I want to be able to just move data around amongst my systems. Maybe it's from my campus clusters to my Blue Waters machine, or from Blue Waters back to other storage systems, or as we'll show in a minute, from Blue Waters Lustre file system to the HPSS to Nearline. Right, so Globus has a model where users can come in and request data be transferred. It's all asynchronous, so you can fire it up, walk away, come back later, and it'll take care of the data securely with high performance. Second major feature, I'll show this, and Blue Waters supports this as well, is sharing. So common scenario, for example, is if you've done a simulation run or on Blue Waters, have a bunch of data sitting in your project file system on Blue Waters, and you want to share this with your colleagues or project team members elsewhere who don't have an account on Blue Waters, this makes it really trivial to do that, and I'll show what that looks like. So again, users can come in, say I want to share some data from a particular folder in my system and share it out to other people. The next capability, which we just announced, I won't show much here, but if you want to learn more, come talk to us, is data publication. We're moving beyond simple file transfer and sharing to also being able to do things like identify the data with digital object identifiers, provide metadata associated with it, provide access control to communities, make it searchable, discoverable, and downloadable. You know, think data publication, whether it's sort of data publication writ large. You know, I have a paper I just published, I need to make the data available, have a process for doing that, or even just sort of collaboration. If you have data that you want to share with your project team, but you still want some of these things like metadata and searchability, identifiers, curation, stuff like that, you know, it works for those scenarios as well. And we do this all as a service, right? So with that, let me just show off very quickly. All right, so got the browser up. Yeah, it looks reasonable. You know, from the logged into the Blue Waters portal, so from there I can easily get to the Globus transfer from the resources page. So we pop that up. It should log you in automatically if you're already authenticated to the portal. If not, you just sign in with your normal PIN and one-time password card. There's two what we call endpoints. An endpoint is simply a storage system that's been connected to the Globus cloud for use. There's two of them related to NCSA, Blue Waters and Nearline. Blue Waters is the Lustre file system, Nearline is the mass storage system, the HPSS. We can use this to do transfers within Blue Waters. So for example, if I go into, I've got a projects folder in here. Let me go down into vendor, Globus. So here's my projects folder. Say I want to take, you know, a particular folder and archive it off to Nearline. Simply select it and hit transfer. And we see down below it's now off and running in the background, moving data off to HPSS. I can also transfer data in and out from other machines. There's getting to be a lot of systems available from University Research Computing Centers available. So for example, this is the University of Chicago's GPFS file system on their campus HPC cluster. So I can say, let's take some data and let's go ahead and create a new folder, call it run 4. Grab some data from here and upload those into that folder in Blue Waters. And again, model fires up in the background. I can shut down, walk away, come back later, check. I see it's already done there. So, you know, they're moved about 300 meg up from University of Chicago to Blue Waters. So yeah, I can move stuff around, and of course I can also do stuff to my laptop. So I've got what we call Globus Connect on my laptop, which connects this machine. So if I want to do downloads, say from Blue Waters to my laptop, I can say grab some file from there. It's waiting for the slow wireless network here to work. So I can download data to my laptop, right? So it just, again, make it really easy to move data around. We can also do synchronization, sort of rsync style replication, so I can move only files that have changed. Now another feature that Blue Waters supports is, as I mentioned, sharing. So in your projects folders, there's a share folder in here, and from that you can do the following. So I've got this directory here, run2results, that is sitting in this folder that I want to share out to other users who do not have an account on Blue Waters. All I need to do is select the folder, come in, hit share. Say, let's go ahead and add a shared endpoint. And I'm not copying any data here. I'm just creating sort of a virtual path or virtual mount point to this place. Right? So now having done that, it becomes really easy to share this folder with any user. I can just email them, say, I've shared something to you. I can search for users. I can share to groups, or I can share to all users. Let me go ahead and share to another user. This SJT demo account is just another Globus Online user who doesn't have an account on Blue Waters. So I just made it so that SJT demo has read-only access to this run2results file using the name Tiki run2results. Right, so that should look a lot like that because it's the same folder. So if I switch over to another browser where you can see I'm logged in as SJT here, I can simply go to it now. I need to refresh to pick up that endpoint probably. There it is. Now I can grab some files out of there, copy them out to NERSC, right? And again, SJT doesn't need any accounts on this, right? So just making it really easy for you to, move your data in and out of the system between Nearline and the Lustre file system, share data out with your colleagues, and then potentially downstream publishing as well. So I'll wrap up there, and I think it's lunchtime. If you have any questions, I'll be at lunch. I'll be around in this evening. Looks like we have one quick question in the back. Okay. So there is a couple options. So the question was, sometimes have too many files, I assume too many files in a folder. You're probably getting into thousands or tens of thousands of files in a folder. So we do have some capabilities through a command line to do things and a REST API for doing more programmatic things. We do have on our list of things to add is some ability right in here in the path is to add some, you know, say, show me only the star dot whatever files, right? So be able to start putting some expressions in there also so you can filter down. It's not implemented yet, but that's on our near-term wish list.